In this presentation, we'll examine how gravity affects the modeling of spring mass systems. In most of the previous examples I've given you, there's been no gravity acting. We've had the masses on a frictionless tabletop, and so we've never needed to consider gravity. Now we'll start to use it in problems, and we'll see how it affects things. So let's start with a simple example. We're going to have a mass hanging from a spring with gravity active. To begin the problem, I'll have just the spring, and the spring is hanging down from the ceiling here. Gravity is acting, but there's no deformation of the spring because our elastic elements are massless. So the spring is now at its natural undeformed length, the same as if it was on a horizontal tabletop. In our next step, we add a mass to the spring, and of course the spring is now going to lengthen and respond to the weight that the mass is applying to the spring. Of course, the weight is going to be mg, where m is the mass of the spring, and the amount of deformation of the spring in response to this weight is going to be mg over k, where k is the spring constant. We'll denote this amount of stretching of the spring as yst, where st stands for the static equilibrium. In step 3 of our analysis, we'll add an input force, which we'll label Fi, and this is acting on the mass with the downward direction being labeled as the positive direction for Fi. We'll define Y as the amount of stretch of the spring due to both external force Fi and the weight of mass m. We measure Y from where the spring ended before any mass was added to it. So now let's make a free body diagram for our system. Here we have the mass m, and we have the weight mg acting downward. And we know the direction that it will be acting. It will in fact be acting downward. Then we have an arrow for Fi. This arrow just indicates the positive direction for this variable. Fi could be acting downward or upward, but if it's acting downward, Fi will be positive. We also have an arrow Fs pointing downward. That says that if Fs is positive, it will be pushing the mass down. Of course, if Fs is negative, it will be pulling the mass up. We'll denote the positive direction for Y, as we saw on the previous page, as in the downward direction. So now we can write our equation of motion from our free body diagram. It'll be m times y double dot equals the sum of the forces. So that will be my double dot equals Fi plus Fs plus mg. And we'll note that if the y motion is positive, then the spring is elongated. Now let's consider how Fs is related to y. If y is positive, the spring is elongated, in which case the spring will be pulling on the mass in the upward direction. And in this case, Fs must be negative, since we described its positive direction as downward. That tells us the relationship between Fs and y. Fs must equal minus ky. With that, we can plug it into our equation of motion, and we'll have my double dot equals minus k times y plus Fi plus mg. We'll now define variable x as follows. X will equal y minus yst. So x is the distance the mass has moved from the static equilibrium position, y sub st. So x is a relative position, and now we'll find the relative velocity and relative acceleration by taking derivatives of x. So x dot will be equal to y dot minus yst dot. But yst is a constant, so yst dot is 0. That tells us that x dot is y dot. And then taking another derivative, we'll find x double dot equals y double dot. That is, the relative acceleration is the same as the acceleration from the original origin. We'll now substitute these equations for x, x dot, and x double dot into our differential equation of motion. So plugging this into my double dot equals minus ky plus fi plus mg, we will obtain the following differential equation. Mx double dot equals minus kx plus fi. And what you'll note is we've had a cancellation here. mg minus k times yst is 0, so we can eliminate that from the expression. So what's interesting about this differential equation? Mx double dot equals minus kx plus fi. You'll note that gravity does not appear in this equation. There is no g. So this is the equation of motion of a mass spring system with an input force Fi, without any gravity present. It's the same equation as if we took away the gravity. We still had the mass hanging from the spring from the ceiling, but there's no gravity. Since it's the same differential equation as if there was no gravity, we know it'll have the same behavior as if there was no gravity. So we can analyze these systems with gravity by ignoring gravity, as long as we measure the displacement away from the static equilibrium position. So, if we measure displacements from the static equilibrium position, we do not need to include gravitational effects in either the free body diagram or the equations of motion. We can ignore gravity. This is a really great result, very powerful, but it will not be true if the spring elements are nonlinear. You know a linear spring element, the relationship between x and F is a line. But for a nonlinear spring element, well, it's a curve. It's not a line. So we can only ignore the effects of gravity if the springs are linear.